Hello again from Digicool Things. After designing my 6809 CPU card, the next CPU on my wish list was the 6502. After building home-built systems in the early 1980s, based on the 8-bit Motorola 6800 and 6809 CPUs, my first introduction to the 6502 was when I bought my first Commodore 64. My interest in making a 6502 CPU card was also due to a desire to replicate the 80s CreatorVision gaming console on an MECB system. The CreatorVision was of course also based on the 6502. Now, I'm a bit embarrassed as it has taken me so long to make this video, as this particular 6502 CPU card design was actually completed at the end of last year. On the schematic that I'll show shortly, you'll see it is dated November 2023. The prototype PCBs were actually received in December 2023, but unfortunately, at the beginning of this year, I was kept busy with flood recovery projects around the house. So the 6502 CPU card PCBs ended up on my shelf, awaiting my attention. So let's dive in by first taking a look at the schematic. As you can see, the schematic was designed in November last year. You'll perhaps also note the similarities with the final version of the 6809 CPU card. The 6502 CPU card has been based on the earlier 6809 CPU card design, which certainly makes sense given the similarities between them. For the 6502 CPU card, I wanted to also ensure I was supporting both the original MOS 6502 CPU chip, as well as the currently still in production Western Design Center W65C02 version. As it turns out, there are only a couple of pin differences that are relevant to us between these two devices. The first is pin 1, which is a second VSS or ground connection on the original MOS 6502, but is a vector pull output on the newer W65C02. Due to this, we need a jumper to allow connecting this pin to ground only when using the MOS 6502. Secondly, we have pin 36, which is a no connect pin on the original MOS 6502, but it's used as a bus enable pin on the W65C02. Bus enable must be pulled high for the buses to be active on the W65C02. To honour the no connect pin on the original 6502, we also need a jumper to pull this pin high only when using the WDC W65C02. The rest of the schematic virtually duplicates what we've already implemented and tested for the 6809 CPU card. This includes our TC1232 reset chip, our I/O request bank select, and the use of our standard ATF16V8 PLD for the glue logic. We also have the same 64 kilobytes fast static RAM chip and our 32 kilobyte 28C256 EEPROM chip. So we have the same memory map flexibility that we have implemented earlier in the 6809 CPU card, and as per the flexible design intention of MECB. Okay, so here is one of the first prototype PCBs, received in December last year. Now seems like a good time to assemble our first one, ready for testing. So let's get some parts out. Okay, we have some parts. So let's start with the lowest profile parts, which will be the IC sockets. Let's get them soldered in. Next we'll do the next lowest profile parts, which will be the resistor banks. Right, we have a 4.7K for resistor network 1 and resistor network 2 is 10K. Next we'll do the 6 bypass capacitors. Next I'll insert the dual inline switch. And I'll do the push button switch for reset. Then the headers. So we have a reset header, we have a 65C02 header, a 6502 header, and a ROM write enable header. Let's get those soldered. And finally, we have the DIN bus connector, which uses two 10mm M2.5 bolts to secure it in place. So let's get that soldered. Soldering complete. With our first PCB assembled, it's time to populate the ICs. First, I'll insert the 74HCT688 8-bit comparator for the IO request bank select. Then our TC1232 reset IC. Next I'll insert the 64K static RAM chip. For our first test, I'll just use a 1 MHz crystal oscillator so that we start out with a clock speed that should work for all chips. For the CPU, we'll start by testing a brand new WDC W65C02 processor. So I'll insert the WDC CPU and we'll also need the 65C02 jumper. So this just leaves our PLD for the glue logic and a ROM. Firstly, let's take a look at the WinCUPL PLD source I've put together for the 6502 CPU card. First we have a standard WinCUPL source header. Then I declare the input pins. Here you'll note that I routed both the oscillator clock CLK and also the 6502's phase 2 output clock to the PLD. The reason for this is to give the choice of using either the 6502's phase 2 clock output or the master oscillator clock as the main bus and timing clock source. This is to allow for backward compatibility, as the WDC W65C02 datasheet indicates that the phase 1 and phase 2 outputs should no longer be used. Instead, the system clock should just be based on your main oscillator clock, that is the phase 0 input clock. It also states that the phase 2 clock output was only used when the clock input pin was crystal driven. In effect, the phase 2 clock output of a 6502 is just the buffered output of the phase 0 input, meaning that other than a small propagation delay, it is identical to the master clock input. So I'll initially be basing the timing and bus clock on the master clock input, CLK, but I've also allowed for using the phase 2 output clock instead, if it turns out to be needed. Okay, next we have the output pin declarations. As noted in previous videos, you'll see that active low signals are inverted at the pin declaration, so that all the logic equations which follow can be based on positive logic for simplicity and ease of understanding. In other words, less prone to making logic errors. Next, I have the logic for generating the standard control bus signals. Again, note I'm initially basing this on the system clock input, CLK. You could optionally change all the CLK references to the CPU_PHI20 signal instead, if needed. Lastly, we have the logic for generating the chip select signals for our onboard RAM and ROM. I've commented out options for 48K plus 16K and 32K plus 32K, so they're ready if needed, but initially I've gone with a full 56K RAM and 8K of ROM. With that explained, I'll now program an ATF16V8 PLD chip and get that inserted. With the PLD inserted, I'll also set the I/O bank select switch to be at E000, which effectively replaces the bottom page of the allocated ROM space. So we have switches 1 to 3 set to off and the others on for bank E0. This just leaves writing some code to enable us to test our initial prototype 6502 card. For this, there was the option of diving into a full monitor program, but as we did in the old days, the best way to test a new microprocessor hardware design is to write some simple Hello World code that we can load into a ROM to test if our design is alive. For a 6502 assembler, I took a look at what was available as an extension for the Visual Studio Code Editor that I've been using for my 6809 assembly code editing. I came across the Retro Assembler plugin, which looks to be currently maintained and also specifically supports both the original MOS 6502 and the WDC 65C02 and others. So let's take a look at my first Hello World 6502 code. As you can see, I've nicely commented it, as I usually do. First, we have a couple of Retro Assembler specific directives Firstly, to ensure we are in 6502 CPU mode, and secondly, to specify a dot pin assembler output format, ready for programming into a ROM. Then I declare the address of our ACIA chip, which resides on our MECB Motorola I/O card. As you'll recall, I set the I/O bank to the E0 page, so our ACIA will be at E008. Or more specifically, the ACIA control register is at E008, followed by the ACIA data register at E009. Next we have the start of our code, where I initialize the 6502. Although not necessary, I think it's good to fire up the system by ensuring interrupts are disabled, we are in binary mode instead of BCD, and that the stack pointer is initialized to the top of the stack, even though we are not using the stack here. Next we initialize the 6850 ACIA chip with a master reset and then setting up the control register. Finally, we have our main loop where we output the hello world string that we've declared below. Note that the string is declared as a zero terminated string, so we can loop through outputting characters to the ACIA every time the transmit register is empty until we have a 0 character. Then finally, we just end in a never-ending loop. So a pretty safe and simple little program for testing a 6502 is alive with a hello 6502 world message. Lastly, in the source, we declare our 3 standard 6502 vectors from FFFA. For the interrupts, we just point to an immediate RTI, return from interrupt. And for reset, we point to the start label at the entry point for our code. So with RetroAssembler, we just need to press Ctrl-Shift-B to build our .bin file. And we have successful assembly. As we originate our code at F000, and we have vectors declared from FFFA to FFFF, we have a 4 kilobyte .bin file output from our simple program. Let's get that programmed into a 28C256 EEPROM. As this is a 32 kilobyte ROM, I need to load the 4 kilobyte bin file into the programmer's buffer at hex 7000 to put it into the top 4 kilobytes of the ROM. With the ROM programmed, let's get it inserted in our 6502 CPU card. Our CPU card is now fully populated, ready for its first ever test. I'll take out the 6809 CPU card, which I've got on the horizontal connector. I'll add some standoffs to our new CPU card, just so it sits nicely. Right, so let's get it plugged into the backplane and fire up our Terraterm so we can monitor the serial output. And we're ready for our first turn on. So how confident am I? Well, with any new microprocessor project, you kind of have an expectation of some debugging required. Note also that with microprocessor projects, with their multiple bus connections, I've also modernised my prototyping approach. Similar to how I've modernised my early 80s wire wrap design to now instead use my MECB PCB standard, I've also taken advantage of modern PCB design tools and low-cost PCB manufacturing to modernise my prototyping process. I now find that, particularly for microprocessor projects, instead of the usual breadboard prototype process, I find it more efficient to just dive straight into PCB routing and going straight to a PCB prototype. So, instead of using a rat's nest of jumper wires on a breadboard and being impacted by breadboard capacitance and inductance. Instead, I only have the possibility of a few cut PCB tracks, a few jumper wires, and perhaps a few PCB iterations. But this approach also fast-tracks the final PCB version by getting into the PCB routing earlier in the design cycle. Of course, the one downside is you end up at moments like these, where you've done all the design work, ordered and assembled the first PCB, and now for the first time you're ready to apply power and see what happens. So here goes. Power on. Well, that's pretty cool. Okay, with that success, let's now swap out for an original MOS 6502 processor. I'll take out the WDC chip and also move the jumper across to the 6502 header. Here's the jumper, so I'll stick it in the 6502 here. And I have a MOS chip, which I sourced from AliExpress. Don't know if you can read that. Let's get that inserted. And I'll plug it back into the backplane and power on again. Awesome, we are still in business. So as I expected, there was no need to update the PLD for the clock source. Well, with that awesome success for our initial MECB 6502 CPU card test, I think I'll end this video here. If anyone is interested in playing with their own 6502 on the MECB bus, with the CPU card now tested and working, you'll now find it available from my Tindie store. You'll also find resources on the MECB GitHub repository. That's it. Thanks for watching.